Hello AAT, this is continuing in Unit 3, Section 3.1. We're looking at the fundamental theorem of algebra, and how many roots in the domain and range of a given polynomial. So here we've drawn this polynomial. It looks to be cubic because I see 1, 2, 3 different directions going on. But it's possible that it could have been more than that. So first we look at the domain. We're going to assume on these that these arrows are going on and on and on. So our domain is all real numbers. We can write that as interval notation from negative infinity to infinity. Or we could also write that as the big all real number symbol. Everything is working. Any x, even if I plug in x's up here, they'll still work because that arrow is going on and on. Range is also all real numbers, because you can see it's going, all these y values are being used and all those y values are being used. The x-intercepts, we got 1, 2, 3, 4, -5. Please write those as a coordinate. -5, 0, 2, 0, and 4, 6, 0, it looks like, are our x-intercepts. We have 3 of them. Our y-intercept, kind of hard to see. Looks like maybe 1, 2, 3, 4.5. We're kind of going to guess on this, but our increasing and decreasing intervals. So our increasing interval means for what x values is this graph increasing? And this graph is always increasing until we get to, it looks like, -1. So we're going to say it's increasing from negative infinity to -1. Remember, we're looking at x values. Negative infinity to -1, it's increasing. And then it's decreasing from that -1 till we get to this value. And that value is 1, 2, 3, 4. So from -1 to 4, this graph is going down, it's decreasing. And then it's going to increase again from that 4 on forever to infinity. And we put a little union here because it's doing it in this interval and also in this interval. Okay? Number of real roots is the same thing as the x-intercept. There are 3 x-intercepts in here. Number of imaginary roots. Well, we don't know the number of imaginary roots. We would only be able to know that if we had the equation for the graph, which maybe we should have been given. So for right now, we don't know how many imaginary roots it has. It depends on its degree. So it would actually be the degree of that polynomial minus the 3 that are there. Relative maximum are your maximum points in the interval. So it's called relative maximum because it's only within the graph that we can see. So our hills and valleys are maximum or minimum. So our relative maximum is at -1, up 1, 2, 3, 4, 5. And our relative minimum is 1, 2, 3, 4, 1, 2, 3, 4, 4, -4. So our highest point and our lower point in the interval. And it actually there could be multiple maxima and minimum at any given interval. Okay, looking at this next one. Again, we're going to pretend like, since these are polynomials, they're all going on and on forever. So the domain of this, again, is negative infinity to infinity, or all real numbers, because every x can be plugged in. The range, however, since this both ends go up, is starting at the lowest point. There's no y values being used below this 1, 2, 3, 4, -4. Only -4 and up has y values working in the range. So we're going to have a closed bracket from -4 to infinity for the range of that. X-intercepts, looks like we got 1, 2, 3, 4 x-intercepts. This one's at 2, 4, -6, 0. We have one at -2, 0. We have one that looks like 0.50. And this is kind of a judgment right now. We don't know exactly. 1, 2, 3, 4, 5, 6, 7. 0. So our number of real roots, remember, is the same thing as how 1, 2, 3, 4, how many x-intercepts we have. Our y-intercept is right in here, which again looks like it might be about 1/2. So we're going to just guess that it's 0, 1/2. Our increasing intervals, so where is this graph increasing this time? This time we're increasing from here to here, and we're increasing here to here. In the other places we're decreasing. So we're decreasing from negative infinity till we get to this value, 1, 2, 3, 4, negative 4. And then we're increasing from negative 4 till we get to negative 1. Remember, we're looking at the x values. And then we're decreasing again from that negative 1 till we get to 1, 2, 3, 4. I think that's 4. And then we are increasing from 4 on to infinity. Okay, so back to imaginary roots. Like we said, we don't know exactly how many imaginary roots by looking. However, if it's this has 1, 2, 3, 4 directions, so it's at a minimum of something to the 4th, but it could be to the 6th, it could be to the 8th, it could be to the 10th, 4th at the minimum, but it could go up by 2 degrees because we know it's both ends are going up, so it's even on that highest degree. So how many imaginary roots does it have? Well, it has the number, whatever the degree is, minus that number of real roots. So if it was a 6th degree, it'd have 2 imaginary. If it was an 8th degree, it'd have 4 imaginary. Remember, imaginary come in pairs. The relative maximum, there's only one of them. That high point is at negative 1, 1. And relative minimum, there's 2. At 1, 2, 3, 4. Negative 4 looks like down to negative 2. And then another one over here, it's just our valleys, which is at 1, 2, 3, 4, 1, 2, 3, 4. 4, negative 4 for that minimum. That's funny, it's the same minimum it was in the previous problem. All right.